morning or good afternoon to everybody attending, depending on where you're connecting from. And thanks for being here today in this wonderful journey towards how BASF can make our world more sustainable with its chemistry. I am really excited to virtually sit in front of such a big, knowledgeable and distinguished audience. And I also wish to personally thank you very much for connecting with us today. Today, we're going to talk about our new platform of heterogeneous precious metal catalyst, which we call green, and which is aiming to make our catalyst sustainable tools to enable your chemistries. But let me introduce myself first. My name is Valeria Stoni. I believe many of you, most of you know me already, and I am the European Sales Manager for sales of heterogeneous precious metal catalyst of BASF in Europe. I have nearly 30 years of experience in catalysis, so I kindly ask you not to start calculating back in your mind what my age might be. And I have a background in industrial chemistry from the University of Milano. But now I would like to leave the stage to our global marketing manager, Dr. Hans Donkervoot. Hans will take you by the end and will introduce you to some very important news on what we firmly believe might be a step change in the landscape of catalysis. So Hans, please, I hand it over to you, and we will all enjoy your presentation.
Thank you, Valeria. I certainly hope, and I'll try to make it as enjoyable as possible for all the attendees. I'm also looking forward to sharing these results that Valeria was already hinting to. Although the start of the presentation might sound a little bit negative, or in the end, I hope that we will be able to share a positive outcome of it. And by meaning negative, I am referring to the big challenge that we are all facing as inhabitants of the planet Earth, that we do have a challenge of climate protection, maintaining the climate, and it is probably the biggest challenge of our time. And we need to limit global warming to provide a future for all of us. I mean, that's a given. And it's a task that we all need to contribute to. It's you, me, everybody personally, but also companies, corporate companies, small companies, everybody. And also BASF, we take up that challenge, and we work to become more efficient in our production processes, focus on reducing our energy usage, or minimize the global greenhouse gas emissions. And we accelerate the development and implementation of new carbon dioxide-free processes. And that we do that all with the objective to limit the climate warming well below 2 degrees C above the pre-industrial levels. And as I stated it before to others, that is essential. I'm living in the Netherlands, close to the North Sea, known for its very nice beaches that you can live on, if you're lucky that the summer is warm enough to enjoy it at least. But if we are not going to work on these climate protections, then sea levels will rise. And although now I'm half an hour driving from the beaches, if we do not work hard enough, I might be able to jump in the sea in front of my the front door. And as nice as it might be, I would not really like to go in that direction. So we do face that challenge, and as I mentioned already before, BASF is certainly taking up on that challenge and the commitment. We as a company commit to reduce the greenhouse gas emissions by 25% in 2030, and reaching in 2050 a net zero situation. And that is really a huge target, and it involves many different disciplines. Continuous improvement in operational excellence, sustainable procurement, production of raw materials, and of course we need to develop new technologies. And we spend significant money in research and development projects that aim all at the development of innovative technologies that could deliver reductions in carbon dioxide emission. And I want to highlight 3 examples that could potentially deliver that reduction in carbon dioxide emission. The first one being the development of a methane pyrolysis process, which would provide hydrogen produced without carbon dioxide emission. And as you all know, in the current production of hydrogen, significant volumes of carbon dioxide are produced. And hydrogen is a material that the chemical industry requires in large quantities as a reagent. BASF is using hydrogen, for example, in the ammonia synthesis. But hydrogen will also be essential for many sustainable energy carrier and energy storage applications in the future. And together with several partners, BASF is therefore developing a new process technology to produce hydrogen from natural gas. And this methane pyrolysis process splits natural gas directly into hydrogen and carbon. And the resulting solid carbon can potentially be used, for example, steel or aluminium production. And of course, the hydrogen we can use in our chemical processes. The methane pyrolysis process requires little energy if compared to other alternative technologies. And if we would then, if this required energy would then come from renewable sources, the hydrogen can be produced on an industrial scale without CO2 emissions. And that's really something that, that would make a significant impact. The second example is about the development of e-furnaces for use in steam crackers. Steam crackers play a central role in the production of basic chemicals, and they require a significant amount of energy to break down the hydrocarbons into olefins and aromatics. And typically, the reaction is conducted in furnaces at temperatures at 800 to 900 degrees C. And today, these temperatures are reached by burning fossil fuels. And with the e-furnace project, we aim to reduce the carbon dioxide emissions by powering the process with electricity. And also for this technology, if the required electricity comes from renewable sources, the e-furnace technology has the potential to reduce carbon dioxide emissions from steam crackers by as much as 90%. The carbon dioxide emissions resulting from the current production methods in the steam cracker could also be significantly reduced by the dry reforming of methane. That's the third example. This process creates a syngas, which is transferred into olefins via an intermediate step of dimethyl ether. And our researchers have now been able to find a way to make that transformation possible by applying new high-performance catalyst systems. And these new generation catalysts are currently being marketed in cooperation with Lindlar. But it's not only internal that we focus. Of course, we focus on internal production processes, but we also want to help our customers to better measure and also reduce the carbon footprint of their own activities and products. And already today, BASF is offering customers products with reduced carbon footprint based on renewable or recycled raw materials. But in addition to that, BASF will provide the customers with total values of carbon dioxide emissions, the carbon footprints, for all our, well, it's stated here, approximately 45,000 sales products. Fortunately, I'm not responsible for all of those 45,000. But anyway, the product carbon footprint comprises all product-related greenhouse gas emissions that occur until the BASF product leaves the factory gate to be delivered to the customer. So it is from the purchased raw material to the use of energy in production processes. And in other words, BASF wants to deliver sustainable solutions for its own production processes. And at the same time, we want to be an enabler to help our customers to reduce their carbon footprint impact. So we reduce our carbon footprint by improving our production processes, allowing reduced energy usage, while at the same time switch towards the use of renewable energy. And together with our partners, these examples of innovative breakthrough technologies are developed which allow efficient raw material production. They enable improved circular economy contributions, and so on and so on. I've shown you already the examples. For example, this dry reforming process where catalysts play a very important role. And catalysts are used in the production of basic and specialty chemicals. Actually, the sheer fact that you use a catalyst instead of a non-catalytic process is already delivering a significant contribution towards making such production process more sustainable. Sorry, that was something that popped up on my screen. So if we use a catalyst, we do make the process already a more sustainable process. And but at the same time, we as catalyst producers and developers, we need to constantly look for sustainability improvements which catalyst can deliver. It's not a point that we are at and we can stay. No, we continuously need to challenge ourselves. And I would now like to move specifically to the field of precious metal-based catalyst and show you what we have done recently in the last couple of years to contribute to a more sustainable future with precious metal catalyst. Because that is certainly not an easy task, and there are many challenges that we are facing using these catalysts, waste reduction, recyclability of those catalysts. We need to get lower carbon dioxide emissions, also using those catalysts. Never forget the chemoselectivity. I mean, the process needs to be selective, but on the other hand, it also needs to be, how do you say, the financial benefits also need to be, it needs to be an economic situation that you can use the catalyst. So the cost of the use of precious metal needs to be manageable. And that is significantly impacting at this moment the use of precious metals. As you can see on these three graphs, the price development of the palladium, rhodium, and platinum catalysts, well, mainly palladium and rhodium since 2016 until now, you see a steep increase of the metal prices, where rhodium is currently at a level of $450,000 per kilogram of metal. And if you that, for example, would correlate to 1 kilogram of catalyst, a 5% rhodium on carbon catalyst, the cost contribution of the rhodium alone is $23,000. So that's from a price development point of view, but there is also a sustainability impact on the use of precious metals. And it was, to be very honest with you, it was higher than I was actually expecting. A full life cycle assessment, which was made recently, indicated that for each kilogram of mined precious metal, 25 to 40 metric tons of carbon dioxide are emitted, depending on what type of precious metal you're using. So with that as a background, we set out to challenge ourselves and develop catalysts that can bring together not only an improved sustainability, but also a good cost efficiency. And that platform of technologies we are going to introduce now, we call it green precious metal catalyst, standing for, well, the capital G for green, the R for renewable, the E for efficient, and then the last EN for enabler. And I hope I will show you later what we on each of those topics can contribute. But before doing that, I want to briefly touch base on how those catalysts are being produced. Very basic, but we take a support, we interact it with a metal, and then you reduce the metal, or you do not reduce the metal. You have a carrier that contains pores, the functional group. If you have carbon, for example, as a carrier, it contains many different functional groups that act as anchoring points of the metal. And those variables are, in principle, they provide problems, but also opportunities for us to control how and what type of catalyst you make. We can change metal concentrations, you can change the metal oxidation state, you can also change the size of the metal crystallite or the location at the pores, in the pores of the carrier. And for example, very well known, but yet I need to mention it, the higher the dispersion, the smaller the metal crystallites are, the higher the metal surface area you get, and typically you obtain also a high active catalyst. That being said, that's not always the case. There are reactions that are structure sensitive and that require a lower metal surface area. So for us as a catalyst producer, it is essential that we can control what we are making, control the size of the crystallite, control the location of the catalyst, which an example is shown over here, which has significantly impact on the selectivity. Going from a mixed metal location where you form 94% of the required product and 6% of the side product, going to an eggshell, you increase the selectivity to more than 99%. So the metal location has also a significant contribution on the performance of the catalyst. And all those concepts we have we put them all together, and we started looking, okay, what can we do to develop new production technologies that can allow us to make the metal even more available, so we can have a higher active catalyst that can contribute to a more sustainable technology, while at the same time also make the use of those catalysts more economically viable. And with that being stated, I would now like to go through a couple of case studies where I hope I can show you what those new green technologies can bring also to you as a user of those catalysts. First example is an example where I would like to highlight the green aspect, and it is focusing on the development of a Lindlar catalyst replacement. Lindlar catalysts are being used mainly for alkyne to cis alkene hydrogenations, and the Lindlar catalyst, for those not completely knowledgeable in that field, is a palladium catalyst that also has been poisoned or modified by a significant amount of lead. And especially the lead component, obviously a toxic chemical, you do not like to use. And the challenge was imposed on our researchers. Can you come up with a replacement for the Lindlar catalyst which will not have that lead anymore? And in the end, this was the result. So they came up with two products, the green LF100 and the green LF200 catalyst, both containing a very low amount of palladium, 0.6 and 0.5% palladium, while the activity on catalyst loading is the same as the Lindlar catalyst. And please remember that the Lindlar catalyst contains 5% palladium. At the same time, you notice that there is no symbol for lead anymore. We were able to take the lead out by controlling the size of the metal crystallite in such a way that the selectivity that is being obtained in this reaction is as high as for Lindlar catalyst, but no lead is being required anymore. So we remove the lead, we have a significantly higher activity, allowing a reduction in the metal content that needs to be charged into the reactor. So when you then look in the scope of the use of those catalysts, you can see there's a quite wide scope where, irrespective of what the R1 or R2 groups are, you get a very good selectivity towards the cis alkene. It can be aromatic alkynes, it can be aliphatic alkynes, and the selectivity is really at a very high level, as indicated in this table. What you can also notice here is that the amount of catalyst, the amount of palladium, I should say, has been reduced by almost, or it is actually 90%. Instead of 2.5 milligrams, only 0.25 milligrams was used in this example. So a 90% palladium reduction while maintaining the same activity levels. So as a result, the green deliverables of this case study is that we have developed now two catalysts that significantly reduce the amount of palladium required, and that is corresponding to a CO2 emission of 90%, or in other ways expressed, 2,000 kilograms, 2 metric tons of carbon dioxide per kilogram of catalyst being reduced. That's the sustainability benefit, but then there's also the economic benefit. By reducing the amount of palladium required in this process per kilogram of catalyst used, you will require less 2,300 euros per kilogram on metal that needs to be procured. So together, really a significant deliverable that comes out of this green platform over here. The second example. The second example is focusing on renewable. Catalyst, precious metal catalyst, as we all know, they need to be recycled. You make the fresh catalyst from metal, and you use it in the process, and you want to get that precious metal back out of the spent catalyst. And BASF is offering a full loop service, so you can come to us for the whole cycle of every aspect involved in that process. In that whole process, though, there is quite a high carbon dioxide emission from mined precious metals. As we all know, I showed it before, 25 to 40 metric tons per kilogram of metal. The majority of catalysts based on activated carbon that's coming from natural resources, and you burn it off when you do the refining. And the refining process is as such, it's a burning process, so it's energy intensive. So what can we do to make these processes more efficient altogether and reducing the carbon footprint of these materials? It is a topic which we are currently working on. I can therefore unfortunately not share yet the deliverables, but we will certainly make that available as soon as we have that concluded, and we will then be able to quantify the carbon dioxide emission reductions and the financial benefits that come out of this project. But it is work in progress. The third example, a reaction which is quite common in specialty chemicals, the Nitro group reduction, which requires a catalyst. You can use that with palladium or carbon catalyst. If the reaction is very basic, where you do not have other functional groups, then for sure palladium can be used. But as the moment you have a functional group in that molecule, then chemoselectivity tends to be rather low for palladium or carbon catalyst. Platinum catalyst you can go to. Certainly they improve on the chemoselectivity, but they have a tendency of building up the intermediate hydroxylamine. That I mean, as we probably all know, the Nitro group reduction is a multi-step conversion into the amine, and the one before final product is a hydroxylamine, which is much more difficult to reduce, and it can build up in your reactor. That by itself is not a problem, but the unfortunate thing is that hydroxylamines tend to decompose explosively. So you really need to take care that you do not go into an explosion regime through the buildup of hydroxylamines. So all those challenges need to be tackled while trying to make the process more sustainable. And what I want to show you here are the solutions that we came up with. We developed 4 new catalysts. They're listed over here, again, coming from the green portfolio, and they are very efficient. They fall under the efficient platform, where we have significantly reduced the metal content. I mean, typically 5% or 3% platinum on catalysts are being used. The last couple of years, we see a very good catalyst, a 1% platinum vanadium promoted catalyst that is being made available. Yet with our catalyst, we are making a further step change towards a lower metal containing catalyst that has an even higher activity and also maintaining still a very good selectivity. On top of that, these catalysts do not build up hydroxylamine. Either you can use the unpromoted catalyst, platinum 100 or platinum 200. If by any chance your substrate is somewhat more difficult to hydrogenate and there is a tendency of hydroxylamine buildup, then you can move to the platinum 200 or 210 that they contain some molybdenum, which is taking care of the hydroxylamine being converted as soon as it is being formed. So you will not have a buildup of hydroxylamine in your reaction. Also, these catalysts can be applied on many different substrates. We looked here at mono, the orthochloronitrobenzene, dichlorobenzene, or a nitrile substituent being present on the aromatic ring. All of those substrates can be handled in a selective way. And what I also would like to highlight here, you can see the amount of platinum, 0.11% versus 0.22%. So you reduce the amount of platinum by 50%, while at the same time you still have a reaction time to full conversion, which is close to half of what is required for the vanadium remote platinum catalyst. So you have double the activity versus traditional catalyst. You can apply it in a very wide substrate scope and still maintain a high chemoselectivity. And let's not forget, because it is very important from a safety point of view, no hydroxylamine buildup in your reactor. So these are the green deliverables for this project. 4 new products that are commercially available, and because of their lower metal content, they do make a good contribution in the reduction of carbon dioxide emissions, 50% versus the standard catalyst, 2 metric tons of carbon dioxide lower for each kilogram of catalyst used, while also bringing this financial benefit that is depicted over here, 140 euros per kilogram of catalyst. That's the case study 3, which I wanted to share with you. We move on to the next one, case study 4, low metal content catalyst. As already you've seen for a couple of examples, lowering the metal content of the catalyst will deliver a sustainability benefit and also a financial benefit. I just remind you of the trends of the precious metal prices, if you would not know, but if we can lower the metal content while maintaining the same activity, making, in other words, the catalyst more efficient, we can make a very good contribution to both of those challenges. And here is an example. The solution and the scope. You can use those the low metal content catalyst production platform can be used on palladium, platinum, and rhodium catalyst, and we can deliver significantly higher productivity catalyst. This is an example in a deep protection reaction. The classic catalyst using a 10% or a 5% palladium catalyst. Here I show the green example of a 5% palladium catalyst. We actually also developed a 3% alternative, which is as active as the 5% palladium. So you can really bring a significant cost saving, while at the same time, due to the lower metal usage, you bring your carbon dioxide emission numbers significantly lower. So the deliverables of these catalysts is that we have now developed low precious metal content catalyst with a high productivity. And an example of such a transformation of a standard catalyst towards a green alternative, which is coming from one of our customers, is they use the 10% palladium with a usage factor of 1, and they changed to a 5% with a usage factor of 0.7. So overall, they could reduce the amount of catalyst on top of the already reduced amount of metal, and overall give a palladium usage reduction of 65%. And that obviously, there's a one-to-one link, so 65% palladium usage reduction, 65% carbon dioxide emission reduction. For palladium, that is resulting in 240 kilograms of carbon dioxide in this specific case per kilogram of catalyst, and the financial benefit of 2,300 euros per kilogram. Another example, now focused on rhodium. The customer using a 5% rhodium on carbon, usage factor 1, a drop-in replacement, going from the 5 to the 4.5% rhodium on carbon, reducing the rhodium content by 10% in the reactor. And here are the sustainability and the economic benefits depicted over here. That is the example of the efficient benefits. Finally, I would like to show you an example of the enabler. what can we do in enabling you to make your process more efficient? We are focusing here on leaching resistant catalyst. As you know, when you use a precious metal catalyst, they can, we provide them as a heterogeneous catalyst, but metal can also go into solution. And that is a challenge, a problem that we need to solve, because it leads to active ingredient impurities, that therefore you need to do additional purification steps. But if you do not get it out of your active ingredient, or if it ends up in your wastewaters, that metal can also be lost, and that would then of course be an economic negative point. So how can we influence that metal, the leaching resistance of catalyst? We can influence that by having a stronger metal support bonding, and that is what we worked upon. How can we make catalyst in a better way that the metal stays strongly attached to the carrier? And the results are shown over here. Again, a different metal deposition technology was developed that leads to significantly stronger metal support interactions. We can use this technology now for rhodium and platinum-based catalyst. And when you use that technology, it leads to a lower metal dissolution. And this is a graph showing you the difference. The standard catalyst, in this case, it was the rhodium catalyst. And if you apply the green deposition technology, you can see that you lower it by 60%, the amount of metal that can go into solution. So the green deliverables out of this project: low metal leaching resistant catalyst based on rhodium and platinum, leading to a lower metal impurity in your product, and as a consequence of that, leading to higher metal returns. And again, a customer example, one based on the rhodium catalyst, or the green 5% rhodium catalyst that is depicted over here was a drop-in replacement for the 5% that the customer was using. Initially, they had 78% metal recovery. With the green solution, you go up to 90%. That is a 12% emission reduction, a 12% increase in metal recovery, and therefore a 12% reduction in emission of carbon dioxide. And the benefit per kilogram of catalyst depicted over here. Another example is on platinum catalyst, where a 5% platinum was used and replaced by the green alternative, improving the overall metal recovery from the process by 9%. And the benefits are shown over here. That is the final case study which I wanted to, the results of case studies that I wanted to share with you. I hope that by showing all those benefits of the new green platform of technologies, that we can jointly, I mean, it is really a joint effort, the customer together with BASF, we can jointly bring reduced precious metals catalyst in use in the market. And by doing that, we are both contributing to an overall reduction in carbon dioxide emissions. We both can then contribute to a higher metal, by having the higher metal productivity, again, lower the amount of metal that is being used in the process, where in the end, you as a customer will benefit from also from an economic point of view. So all of these components out of the green platform, they deliver carbon dioxide emission reductions and significant cost savings. And with that, I think we really can, both the customer, you and us, we can move from what we did in the past, dream about a green initiative. We can jointly move towards act green. We can implement, use those technologies, and really make our contribution. And with that, I would really like to thank you for your attention. And if there are any questions, happy to answer.